probably are just very clear results in modifying the surface albedo and cloud radioactive properties. And probably will be continuation of the previous one, or we will see.
So apologies if you weren't at the previous talk. I'm going to assume that most people were, so we're all happy with this idea of albedo. So the geoengineering one is a very general topic, and it's one that I've given a number of times on this, and actually quite an interesting one. I know bits about it, you know, the science sort of feeds into it, but it's not actually something that I research. So this is more something that, you know, I have done over quite a few years, various things flying on aircraft, and looking at the repercussions of atmospheric mineral dust and all the ways it affects. So it has lots of different effects in different timescales. So immediate timescales and then long-term timescales. So I didn't know whether I suggested that Boris could come up and talk about some of my slides, because some of this is his PhD. So he was recognising computer models that we've got in that. So I'll start off very, very basic. So, and this is sometimes there's some fantastic diagrams that help people think about things. So now, when I say mineral dust to some people, you know, it's easy to say sand to people, because that's generally what people think about. And dust, if you talk to your mother, is what she does. That's dust. Okay. So a speck of dust is halfway between the size of that and that. So how many people in this room going, yeah, and they're just doing the maths, thinking about it. So the first thing I do goes, well, yeah, that sounds, but that's really small. That's really big, and I know that's really small, okay? But, done it, I did the maths, atomic diameter, and a 500 micron speck of dust is about halfway between that and that. So, maths, I'm happy with that. But that's household dust. So, atmospheric mineral dust is 20, 50, 100 times smaller than that. So, but that's always just a nice thing, you know, when you say things about small, and you think about, you talk to people who aren't scientists about different quantities, an order of magnitude. People don't know what an order of magnitude is. 2 orders of magnitude. A billion, a trillion. You know, to an American and a European, a billion and a trillion are different. So, and the size is very important for a number of different reasons. So, from an air quality perspective, the smaller it is, the deeper it goes. So, if you breathe in household dust, it stops here. If you're, you know, doing DIY, drilling, things like that, producing large particles, your body filters it out here. The smaller it is, the deeper it goes. This stuff is small enough to pass into your bloodstream. And this stuff is very small, but it's not the fact that it's really small, it's what's stuck to the surface. So this is black carbon, and black carbon is a fantastic filter. Things stick to it. And the things that stick to it are called, certainly from cars, they're called polycyclic aromatic hydrocarbons. They sound toxic, and they are very, very toxic. They are difficult to buy, they are that toxic. So, and it's the fact that these things are stuck to the surface, and they slowly dissolve into the bloodstream. But with mineral dust, and these are produced by high temperature reactions, gas molecules bonding together, getting bigger, and you go from a gas to a particle. So they're sort of growing from the nanometer scale. But for mineral dust, that's produced by basically rocks banging together. And you keep banging them together, and they get smaller and smaller and smaller. But there's only a finite size until they simply have not enough momentum, inertia. When they bang together, they bounce off. So you don't really get much mineral dust much below about 250 nanometers. A lot of that's still small enough to breathe in, but it doesn't have all this stuff to it. So lots of people, if they know there's going to be a Saharan dust outbreak, they'll see it, and they'll do that to the car, and their finger will be yellow, and they think, oh, we're all going to die because it's the Sahara dust. But actually, it's nowhere near as toxic as this. It can give people breathing difficulties, but as a material, it's relatively inert compared to the toxicity of what comes out of the back of cars. So, and mineral dust, there's a huge distribution. So this is a nice one for geochemists, and a lot of people in this room will probably be quite comfortable with this idea that, you know, there's a lot of mineral dust. But that's changing a lot because we're changing it. We're geoengineering the mineral dust availability. So we're chopping trees down. We're overgrazing areas. There's erosion and all those sorts of things. And this is just looking at sizes below 2 microns. So you can see there's quite a wide variety of that. And there are some places that are phenomenal sources of mineral dust. So this is again the TOMS satellite, and this is an aerosol index. So, and this is showing Africa, and this is a place in Chad called the Bedeli Depression. 5,000 years ago, it was a lake. It was so big it was known as Lake Mega Chad, but it's now dried out, and everything that settled down to the bottom is now, and it's between, there's 2 mountains here, so the wind blows down it and it lifts a phenomenal amount of material up into the atmosphere. So you can see it, you know, it's one specific location that is a huge source of aerosols. And this is the answer to your question, Boris, whether with increasing energy in the atmosphere, are storms that are going to increase, that lift this sort of stuff, are they going to increase? This is a model, so this is looking forward at 100 years hence, this is looking at the end of 2100, and this is the base of the wind speed, and you can see that we've got this distribution, and it's just like extreme events, where they're all going, so they're becoming more extreme and happening more often. So in answer to your question, yes, or according to that model. But there's lots of people run lots of different models, and all the models are agreeing. So, and as you know, if everybody in this room has a different approach to something, different way of measuring something, but we all get exactly the same answer, that's a very difficult thing to argue against. So, just returning to this, I hope you remember this. So again, we're now looking at this mineral dust has got its own area. So this is sulfate aerosol. That is industrial sulfur dioxide. We've got nitrate aerosol. We've got organic carbon. This is black carbon. This is the dark stuff in the atmosphere. So remember albedo. I don't need to go on too much about that. So I'm just planting the word there again. And another word that Boris mentioned me, sounds like the Boris show now, isn't it? But he mentioned about haboobs. So haboobs are this incredible meteorological phenomena, but they're not limited to Africa. People tend to think they're Africa or the Middle East because they've seen the film The Mummy. That's a haboob dust storm. But they happen a lot in Australia, places like Texas. So what happens here, so this is a large cumulonimbus cloud. It rains, but as it's raining, the water droplets evaporate and cool the air around them. Talking about latent heat. So then you get these big, you get the rain here, and then you get this big gust front coming out, and it just lifts it up, and you get this wall of dust coming out. And that's called a haboob. So that's one picture. Another one that people might have seen, this is quite a famous one from a project called AMA in Africa. It was in 2006, and it shows that how often these things happen. Because if this never happened before, he wouldn't be there. He'd have run away. He would have thought the world was ending. These are reasonably commonplace, you know. So he's getting herding the goats away, you know, because he knows about this. Doesn't necessarily understand the physics of it, but you know, this is not a unique thing. They do happen, and they lift. The ability of these to lift phenomenal amounts of mineral dust up into the sky, high up into the sky, is quite incredible. And you can track. So there was a storm in 2005, the year before we went to Africa for this project, and the student who was there was in Benin. And if you track that storm, it went all the way across the Atlantic and became Katrina. So This is where Americans suddenly start thinking we should understand the meteorology in Africa because it produces the hurricanes that influence the Americans. Americans tend to, more so than the rest of us, I think, but tend to think about how it, certainly the politicians, they only want to understand what affects America. And then suddenly they saw this, and people have been telling for a long time, teleconnections, we think we need to understand global weather, and we could track this storm that turned into Katrina as it went all the way across America. So now this is another storm. Now you've got to get your head around this because north is now, in the orientation, north is now going this way. So in your head you need to rotate this around. So this is the Canaries, this is Africa, this is the Cape Verde, so this is Africa's going to rotate around. And what's happening here, along this line, this is the satellite looking down. So the satellite can actually see the dust in the sky. It's seeing the high cloud here. So it's seeing, now what's happening there underneath is actually not as much sunlight is getting to the surface. We're also seeing the low clouds here. And what happens when less sun gets to the surface, the oceans don't heat up quite as much, so you don't get this the sort of heating effect. And this is where, so an American news network, it'll suddenly become a news story when the dust gets all the way to Texas, but they don't really care until it actually does that. But it just demonstrates that sometimes even the Americans listen. So you're getting increases of Saharan dust in Croatia. Assuming it gets on the news when Saharan dust is coming. But this is something that happened earlier this year. This is this dust outbreak coming up. I'm sure you got some of this. So you can see going all the way around. You can see the different colours, the albedo. This is Sochi. So, made famous by the Winter Olympics. People still skied it, but you can see that's an awful lot of material. That's a ski resort. It's all been covered. So this material is happening there. So, and it's happening now. So this is, you can get this yourself. So this is the Barcelona group. They have a dust forecast. This is the aerosol optical depth. So this is adding up all the dust in the entire atmospheric column. And you can see the Bedaly depression is doing exactly what the Bedaly depression does. It's kicking out huge amounts. And they're just travelling out. Now, a lot of them will be raining out here because it's a lot of it's removed by rain. And also there's so much material coming out of it. It's like if you go to the beach and pick up some sand, if you throw it in the air, the heavy stuff lands fairly quickly. It's the light stuff that travels a long way. So a lot of this is just falling out because there's so much energy lifting it up. That lifts up quite a lot of large particles, so they don't travel very far. Their lifetime in the atmosphere isn't very big. But there are, you can see, and this is only going out this far, but Brazil's only here. It's not very far. And again, another example, just it's mineral dust, it's albedo, but this is Spain. So you can see this is just one storm landed, and you can imagine if you own a ski resort and this happens, that's make or break. That could be the end of your ski season, your business, if that happens. So thinking about dust, and we've already talked about some of the different timescales that we're thinking about, but I'm going to start thinking about just timescales. So instantaneous timescales. So if you have a dust storm where there's a big centre of population, suddenly there's more car accidents. So now we're thinking about a social impact, car accidents, people going to hospital, aircraft are grounded, people with breathing problems. So the effects are very, very quickly. Now they have these models so that they will inform hospitals so they make sure there's more nurses available in accident emergency because there's going to be more people coming in due to all these different car accidents, breathing So there's a big feed through for people understanding this, just to advise different organisations. Crops, so if you get dust falling on crops, it can make them, you have to, is it feasible to actually wash these crops before they're harvested for people to consume, or is that just too expensive? So there's all sorts of damage there. There's the social consequences, so people get very upset because they see Saharan dust and think, oh, it's horrifically poisonous, whereas actually it's the pollution from the cars that they really should be worrying about. It doesn't happen very often, but I guess for atmospheric science it's quite good, because then people go, oh, so they want to know more about it, so it makes, it gets it into news articles and things like that, but it's very visible very, very quickly. And this is one thing with pollution these days. A lot of the pollution that people are concerned about, you can't see pollution anymore. In the old days, in the 1950s in the UK, they had what are called pea super smog. So the smog was so thick, people had to use torches. You had to drive around in your car with headlights on during the day because the pollution was that bad. 4,000 people died in the UK in 3 days in the 1950s. And then they said, right, we've got to stop this. We're bringing the clean air out. So, those sorts of things. But now, because people can't see the pollution, it's not as obvious, people don't really care about it. And then they suddenly care about it if Saharan dust is arriving and they do this and their car needs cleaning. So then thinking about the aerosol cloud interactions, already mentioned earlier on about how these things interact and produce more clouds. But clouds, then you get rainfall, so you've got the impact of are you going to get, from an agricultural perspective, the idea of solar shielding. So we thought about previously, just looked at the effect of geoengineering on crops, those sorts of things. Very quickly, solar shielding has all sorts of repercussions because it can affect the albedo if you're looking down. So this is one forecast. This is a dust forecast from the Athens group, and this is showing a big outbreak of dust going across from Africa, and there's lots of dust in the Sahara, all the way across and sitting over the top of the Gulf of Mexico. Now, one huge effect that has is that then the sun is not hitting the surface of the ocean, so the ocean is not heating up as much. And when hurricanes, when these come across, and if there's a storm system as opposed to the dust, because the dust storms form here, and then you get a storm system going across. The storm systems get here, and they pick up lots of energy from the Gulf, and that's what gives them the energy to go inland. Because as soon as the storm goes over the land, it starts to lose energy because it's interacting with the surface roughness. But if it's got picked up lots and lots of energy here, it's got more energy to keep going inland. So actually, there's a cooling effect, and that's shown. There's a very strong correlation. It matches exactly with the models, but people always want to see that the models are doing exactly what the atmosphere, or the atmosphere does exactly what the models do. So when there is, if you look at the integrated amount of dust over the Gulf of Mexico and compare it to the intensity of hurricanes and the number of hurricanes, you can see a strong correlation. So the more dust, the less hurricanes there are. Although hurricanes become big news items if they go through a city, so you can get a huge, very strong hurricane system. But if it goes inland and doesn't hit a city, it's not any news. It doesn't really matter to people. But if it goes to a city, then it does become big news. So there's a balance out on that. You want to look at the meteorological data, not the news items. So, with dust over the surface, so this is just Google Earth, and we've got the Sahara here, lots of different colours. It's not all the same colour. You've got the sort of more equatorial vegetated regions, and you've got the darker ocean. So now if we put dust in the atmosphere over this, it doesn't really affect the colour of that, the albedo of this. But over the oceans, because it's reflecting, it's increasing the albedo over the oceans. So very quickly, you've got less impact of solar radiation landing on the surface. And that's exactly what we can see here. So this is another satellite image. Now this is showing the sea surface temperature. So this satellite measures the surface of the sea, the surface temperature of the sea. And here we have Cape Verde, and there's been a big dust storm that's come out here. So over this region where there's been a lot of dust sitting over the ocean, reflecting incoming solar radiation, less heating of the sea, you can see that. And that's, if you take that area and a single dust storm is putting a 3-degree temperature differential in it, you can see there's a big effect there. Now this one is just due to there was a big storm, so this is dust. This is just a storm system up here. So a lot of this is driven. If you look at this in relation to meteorology, you'll be able to explain all these from meteorology. But this is actually a dust storm. So it just shows the effect of that. And if the dust gets all the way over to here, you get a similar effect. Not quite to that degree, because this will get diluted as it goes out. And some of the material that's in the sky, in the air there, will have been deposited to the surface. It does have a lifetime in the atmosphere. So that's looking at fairly short term, but days and months, this stuff is going to fall out of the sky. It doesn't stay there forever. So, and when it does, going back to the geoengineering, now we've got minerals. Now these are natural minerals. This isn't something we're putting into them. So we get phytoplankton blooms, and ultimately this will, these sorts of things will affect the oceanic circulation, turnover times, and I put snow there. So snow to an oceanographer, are there oceanographers in the room?
Go on.
So snow to oceanographers is different to snow to a skier. Snow is a sort of material, it's sort of dead material that drops down to the bottom of the ocean. And the good thing about that is that's carbon. A lot of that's carbon, that's taking carbon out of the system, dropping down to the ocean. And once it's right down at the bottom, 5,000 metres down, it stays there for a very long time. But it does affect these circulation times. And you've got oceanographers around here, so if you think I'm talking rubbish, go and they'll tell you I'm not actually talking rubbish. But they'll tell you more about it because they know more about it. But it does have an effect on this, and the phytoplankton blooms. And we can see there are loads and loads of different examples of this. And there's lots of examples of from Africa. But this is a very nice one, because what happens, so this is a dust storm in the Gobi Desert. So dust isn't just Africa. People think dust, they think Sahara, and that's the only place. But there's places, Patagonia, the Gobi Desert, there are lots of different sources around the globe. So there's a big dust storm here, this is Beijing, and the wind patterns. Now there was some pollution, but pollution doesn't tend to fertilise the oceans as well as mineral dust. So this is the event. So they had a monitoring station here. So they saw, this is PM10, this is particles coming through, this is all particles below 10 microns. So they saw this event, this is the background, I don't know what that is, 30, shot up to over 500, something definitely happening. If you'd done that, your car would be covered in muck. And then a few days later, they saw a big signal on chlorophyll A, phytoplankton. Particularly this was important because this region is a sort of nutrient, from a nutrient perspective, it's a fairly dead zone. So it meant that in a nutrient limited, if there's a sudden increase, there's something definitely happening there because it's unexpected. And then satellite image, just a visible satellite, and you can see this phytoplankton blue. Also, back to the albedo, that's changed the colour of the ocean surface. So you can see that these things are all tied together. And you can look at all sorts of, so there's all sorts of effects on the general circulation underneath. So this is looking at a study over the Arabian Sea. So they've looked at all sorts of nutrient cycling and things like that. And what they've also done is, because we have measurements from a number of years now going back, not just 1 year, like I said, if everybody in this room did the same simulation model, trying to measure the same thing, but in a different way, and we all measured it and got exactly the same answer. In the same way that if you look at 1 year and show a certain feature, people are going to go, yeah, what about last year? 2 years ago, I remember it was really hot or something. You know, in the same way that the fact that it snowed in Washington 10 days ago proves that climate change is rubbish. Donald Trump told me that. Okay, California, unaware of that. And California is because the Californians don't rake their forests like the people in Finland do. You know, so people are taking these tiny little stories and not thinking about it in the big scale. So this has got nearly 10 years worth of data. So they looked at heavy dust years, 1, 2, 3, and looked at this square, and they've looked at phytoplankton and compared it to less dust. So that's where there's less dust, and that's lots of dust. That's not a difficult thing to defend and say there's got to be something there. That's not just luck. So, and it's not just limited to, I said we got Sochi. You get Saharan dust arriving in Croatia. In the UK, people think the Sahara, that's a long way away. They don't think about the Sahara. But this is Saharan dust plume travelling up the UK, and we're getting, so these fantastic patterns here are showing ocean currents. Phytoplankton is brilliant for showing carbon vortices and things like that, and ocean currents. So you can see these, they're very, very clear. So this is going up to Spain. So this is they go a long way north. We do get about probably 2 a year that are newsworthy, that the papers write. And there was one about 4 years ago. There's a picture of the Prime Minister's car, and someone had drawn their finger down it, and it had Saharan dust on it. So that's worth being on the front page of newspapers, because the Prime Minister's car got Saharan dust on it. So, but it does make people aware of these sorts of things. So there's a. So, and then beyond months, mineral dust, as we've already seen, for phytoplankton is a very effective fertiliser very, very quickly. But it's full of phosphorus and iron and all sorts of minerals that plants need. So, and this has shown that 80% of the minerals that feed the Sahara, feed the Amazon's continually growing, so it's not like, it needs a continuous source of fertiliser. That 80% comes from the Sahara, and half of it comes from the Bedeli Depression. That tiny little pocket shows how effective and how nutrient rich that part is. So this is, and so they've just put some numbers on it. Difficult for some people to, but hopefully you can appreciate it. The Bedeli Depression is a 200th of the size of the Amazon, but provides 50% of the nutrients for it. So if you wanted to go and get some fertiliser for your garden, the best place you could go is the Bedeli Depression, a couple of buckets of it. So, and the Bedeli Depression is only 2.2% of the Sahara itself. But that's just demonstrating what a phenomenal source of dust it is, and actually showing the amount that's transported, 40 million tonnes of dust blows across the Atlantic every year. So it's not surprising, we get some of it. So, and as soon as people start getting these facts, they start to put numbers in, like, if some, when someone told me a speck of dust is halfway between an atom and the planet, I started playing around with numbers. But so the Bedeli emits dust at 40% of winter days. So that's 0.7 million tonnes of dust coming out of this area. That's 0.5% of the size of the Amazon. What we actually need is that as an area of Europe. Whether it's a district, whether it's just how big it is, because even that you can't feed that sort of area into. A lot of people talk about a glacier on the size or a scale of Manhattan or something like that, a sort of tangible areas on. So that the only thing this is missing is actually saying how many football pitches it is or something like that, because that's how people understand. Because we don't, the Amazon's huge, so 0.5% of the Amazon is still a very big area. I think we're happy with that. But just demonstrating that that's another timescale, that's a seasonal timescale. And this stuff travels across, it takes a few days to get across. and it has to get down to ground and then be weathered. This stuff is not, dissolvable, soluble fertilizer. It has to be weathered in the soil and things like that before it becomes what's called bioavailable. So, but that's all the repercussions when it's, lots of it's when it's come down to the surface. But just to think about, back to the, I'm an atmospheric scientist, so I'm going to get a bit more atmosphere into this. So we've got this diagram again, and we're thinking about how it's interacting with the clouds. Now, a lot of this, an important thing, is that very quickly as you go up through the atmosphere, it gets below zero, very, very quickly. So, and below zero, there's still lots of water vapour. So water vapour, pure water, doesn't actually start homogeneously freezing until about minus 33 degrees. So when you're taught the freezing point of water is zero, it's not, it's the melting point. If you get very clean water, it stays liquid for a very long time below that. If you get some mineral water and put it in the freezer, you can get to minus 10 and still be liquid. And you can freeze it just by taking it out and pouring it on the surface that's dirty, or you can bang it on the side. Then a percussion will start the nucleation through that. But it's important because we've got to understand, below 0 degrees, it's not cloud condensation, but it's a process called ice nucleation. And mineral dust, different types of mineral dust are quite good ice nucleating particles. So this is one of the things, and they're not, this is a new thing that is not very well understood. So this is one of our focuses in Leeds. It's the IPCC report does not include ice nucleating particles because there's just not enough knowledge on it yet. The IPCC report is a digest of lots and lots of papers and people's information. So, but IMP will be in the next one to some extent. So, ice, there are 4 different processes. So we get contact nucleation, immersion freezing. There's deposition, so it's just on the surface. You can think about it as a sort of reverse sublimation. And then below about minus 33, you get homogeneous classical nucleation theory. But these require some level of intervention from another particle, an ice nucleating particle. This is pure water. When we say pure water, we mean ultra, super pure water. So, but one of the problems is that IMP are very, very low in concentration. So we saw the CCN with the lighter, with the cigarette, but IMP in the atmosphere are about 1 million times lower in concentration. And they're actually quite, there are very few measurements of them because they're in such low concentration, you have to have a very clean system before you can see a signal from this IMP. If you've got something that's in high concentration, you can accept a reasonably dirty environment to see this. So how do we actually measure them? So I'm going to go back to this. So atmospheric chemists, entomologists studying insects. So we collected insects, microbiologists, meteorologists, and skydivers. So if we want to put instruments and make measurements from 28,000 feet, because this could only go up to, let's change that into meters. So if we want to make measurements up to 9 kilometres, this could only go up to about 2,000 metres, 2 kilometres. We take ex-military bomb disposal bloke, strap instruments to him and throw him out of an aeroplane. It's what you do for television. So, and he'd never done a high altitude skydive. So when he came down, he'd been in the air for half an hour and he'd been hanging in the straps. And when he hit the ground, he fell over. And he panicked. And he suddenly realised he'd just got, his legs, the blood, he had no circulation for his legs. When he realised that was okay, but for that moment in time he thought his legs had just stopped working. But yeah, so that's how we did our measurements. But I'd do measurements, I'd attach them in the airship. But one of the things I wanted to look at was actually how clouds form and different things in the atmosphere. Some are really good at making clouds, and some are not so good at making clouds, and some are rubbish at making clouds. Okay? So, one of these people regularly appears on television. So when they go, look like a serious scientist, he pulls that face, and that's my serious scientist face. So what we're doing here is we're looking at different particles. So I've got some mineral dust in here, and he's got some bacteria, some biology. Microbiologist against the chemist. You know, it's television. They want to, this battle between. So this is the instrumentation that we use in the lab in Leeds. So we're just setting it up. So and this is just basically a cold stage. So this is just a cold plate that we call it. So it's a surprisingly simple experiment. You just have to make sure everything's very clean. So we have this cold stage. We put droplets onto there. We've got a glass slide. Sometimes we collect samples in the atmosphere by drawing air through a filter, and then the material's stuck on the filter, and then we put these droplets on. So, and these are just droplets of very, very clean, pure water, and then we just cool it down, and we film it, nothing more. So this is a cold stage that cools down and it goes down in a very controlled manner, 1 degree a minute, and we've got a €50 webcam looking down on it, just recording it, and then we look at the time that it freezes, and obviously we know the temperature on the time scale, so we know what temperature these droplets freeze at. So for this experiment, because you just make it very, very simple, so this is ultra pure water. We've got mineral dust here, so this is water with some mineral dust, and this is water with bacteria in it. So the bacteria we're using there is called Snowmax. Now Snowmax is a commercial material used in the ski industry. It is a deactivated bacteria. They add to water when they make snow because it just makes water freeze better. So that's exactly what it is. So now this is the filming. We haven't got you don't have to worry about the not having the sound. So I can talk.
First row near me is pure water, and then the second row has mineral dust in it.
That's pure water, mineral dust,
bacteria that we know does live in clouds.
bacteria. And we measure bacteria in clouds, we know it's there.
Yeah, exactly.
All frozen, none of the others are frozen yet.
Mineral dust finally start to freeze. Oh, there's, almost minus 11. Some of the mineral ones are going.
And just
First row near me is pure water.
so pure water, very clean,
Second row.
mineral dust, and this is the bacteria. So
And third row.
that's his team, that's my team.
Does live in clouds.
So they've all frozen a lot sooner, so they're much better
Does the mineral dust finally start to freeze?
at producing as IMP. Although they're much better, but they're a million times lower in concentration. So actually, you can see that there's a two-sided story to that. So it's critical that we understand the availability of these and also the types of minerals and where they are in the atmosphere. So this is coast of Cape Verde. We're all quite happy with daily depression under here, if you remember. So making measurements on the aircraft. We've also got the radar. So this is the cloud radar, so it can tell us where the clouds are. So it takes images of the clouds and it sends them to the aircraft so we can fly to where the clouds are. So makes it much more efficient. And this is off the coast of, this is Cape Verde a couple of years ago. And the first thing we have to do is make sure that we have our system, we have to check it's clean. So we do what we call blanks. This is just putting pure water on them, and they start to freeze. It's very difficult in a hotel, using a hotel as a laboratory to get it super clean, but you can see that there's quite low temperature that they're freezing. Now this is just pure water.
Did you fly all the way to Madeira or just at the coast, African coast?
So it was based in Cape Verde. So the aircraft flew down and it was based there for about 3.5 weeks. And then we just did various flights going out in different directions, depending on where the weather was. So, and then we'd come back to Cape Verde. So we were based at Cape Verde. So now, and these are the samples that we've taken by drawing air across a filter. So we've got the dust, everything that's in the air, above a certain size, we've captured, and then we put the droplets onto the filters. And we can see that that's the blanks, so clearly we've got something that's freezing. So this is quite, so we've got the fraction frozen, so nothing frozen, everything frozen. And this is starting at -5 going in this direction. So this is cold, so this is very warm. This is very warm in this sort of scenario. And you can see that nothing starts freezing, then suddenly you get a very, over a short period of time, they all start to freeze, as we saw in that video. Once one starts freezing, the rest will start freezing very, very, very quickly. And you can get a lot of information about the steepness of these curves. But you can see they're not all the same, so we're getting different concentrations, we're getting different efficiencies, some of the mineral dusts, some of the air from different places, because as you saw Africa, it's not all the same colour, so it's not all the same mineral. So we can see that we're getting a huge range here. So, and this again, now we've changed it into, because we've measured the volume of air going through, so this is now the concentration of isonucleating particles per standard cubic metre of air. We put it in standard cubic metres of air because the aircraft changes height and the atmosphere changes density, so we have to do a correction there. And then what we've got here is, this is back trajectories. So back trajectories, so what we've got here is each one of these that's where the sample was collected, and then we've looked at the history of the air where it's been, so we can see where it's picked up from. And we can see that sometimes, if it's coming over here, it's more likely to have been influenced by dust, and we can see that these track over onto these ones, and then some of these, this is clearly different bits of weather. So you've got a weather system coming down in this direction, bringing air down there, and it's quite good because it's good to see changes. And then you've got more information to explain this away with. And it shows that, so you've got people collecting samples, putting little droplets of water, and then running computer models. So you can see that people having to talk to each other, people, lots of different skill sets here. And then, so this is a PhD student, Alberto. So that is not the Sahara, this is in Alaska. So we go to different places and look where they are, the concentrations are around the world. So we've got Alaska, Iceland, UK and Cape Verde. And you can see, as you'd expect, they sort of cluster around. So in Cape Verde, they freeze at a higher temperature. And when we say higher temperature, you get used to the fact that -16 is a higher temperature than -20, although your brain doesn't really process it. And you can see that as you go to places like Alaska, it's the concentration and also the efficiency, how good they are at isonucleating, changes. So we need to be going to lots of different places and measuring these things. But from a geochemistry perspective, what exactly is mineral dust? Because I'm a chemist, fairly simple chemist, and I say to a geologist, so in our school we've got geophysicists, we've got geochemists, we've got microbiologists, we've got atmospheric scientists, we've got climate scientists. So if I say to the wrong person, they're all just rocks, they're going to hit me. And other people go, yeah, they're just all rocks. So, and this is Feldspar. So Feldspar is a very predominant mineral, and it's one of the ones that's been identified as being a very effective isonucleating particle. And you can see, so the distribution, the abundance of them across the planet is very, very different. And this is just looking at Feldspar, potassium Feldspar, and then comparing it to lots of different minerals. So quartz, mica, calcite, montmorillonite, kaolinite. So even different minerals, they're all very, very different. You can see that Feldspar is an effective, this should actually be on a Celsius, because it's hard enough doing negatives without having to do it in Kelvin. But you can see this is in the same, so this is homogeneous freezing, and this is, as you go in this way, they're getting more and more effective. The more effective they are means that the lower down in the atmosphere they start to produce ice. If you have to go higher up into the atmosphere, you're having this larger and larger area in the atmosphere where the ice is not forming, so you're not getting these clouds. So, and you want to understand how all these different processes are mixed together, because we have this idea of mixed phase clouds, as well as water ice, liquid ice, and solid ice. And one thing we are doing now is actually looking at the chemical composition using scanning electron microscopy, and we can see this is going from about 4.4 microns up to this is the big stuff. Anything bigger than that doesn't last very long in the atmosphere because it's just too heavy. It falls out of the atmosphere very quickly. And you can see that you're getting different composition across these. And this is some samples from Barbados. We've got some different types of samples from 3 different locations, and you can see that in an urban environment, most of it's carbonaceous, like carbon and stuff that comes out of cars and things like that. Mineral dust, you've got a lot of luminosilicates. There's a lot of luminosilicates in the Icelandic, but there's quite a lot of the sodium in this smaller fraction. So for a compositional geochemist, this is fascinating stuff. So that's why we're talking to the geochemists. They're telling us, they look at that and they tell you a lot of things, and then you tell them where the air's coming from, you tell them the history of it, and you put together this sort of jigsaw. Now, when I've talked to some geochemists about this, they are fascinated by this, because to me, quartz is quartz. Again, apologies to any geologists in the room, but these are all quartz, different quartz. And this is the ice nucleating ability of them. So there's a huge range, even for one small group of minerals, quartzes. So that, there's every time you look at something, there's more to look at and more to look at. And this is what we're sort of doing at the moment. And then looking at models. So this is a model looking at Feldspar being transported. Feldspar's IMP being transported. It's a global model run by a lad who used to be doing his PhD in Leeds. And you can see that a lot of it, as we've already seen, is feeding across the Atlantic, going to these regions. A lot of it, as we've seen, has been landed on the Amazon. And so we've made measurements here, but actually what's happening over here? So the next thing we go, we think about downstream. So another team we have a shipping container, so like a mobile laboratory, and they went to Barbados for 6 weeks, and they measured the IMP on the other side of the Atlantic as it travelled across the Atlantic. What's happened to it? The atmosphere is like a chemical reactor, so we want to have a look at how that's changed. So what we've got here is this is the fresh dust, or relatively fresh. In the scheme of things, this is fairly fresh, relatively fresh, Cape Verde. By the time it gets to Barbados, it's much less efficient as an IMP. So this is where there's something there, because all those measurements are confirming the same thing. And this is not super fresh. This is not from a dust storm. This is maybe 2 days after the dust storm. It's been in the atmosphere for a couple of days. So the really big stuff, material has fallen out. So what's changing this? Is it changing the pH in the atmosphere? Something gets, as water condensed onto a surface, and then you change the pH as it dries off, as it evaporates off, the pH can drop remarkably, so you get very, very concentrated acids, or concentrated from an atmospheric perspective. As it's going across the Atlantic, is there some sort of mixing? So what we think is feldspar, what we think is mineral dust is not, it's a mixture of things. Or is this feldspar, is it preferentially being removed through processes as it's being aged through the atmosphere? And these are the sorts of things that we're trying to get a handle on, and this is where, again, talking to geochemists, because they know all about the weathering of cave feldspar and how cave feldspars after time converted into clay minerals and things like that. So what I've done there is hopefully given you some things to think about, how all these materials go up into the atmosphere, and if you see there's been a dust storm, now you'll start thinking about how often that happens, repercussions, all the different things that have landed on it. The numbers associated with how much nutrients, they're phenomenal figures. how much nutrient comes from such a tiny area in Africa and has such a huge influence on the regions, 50% of the Amazon and things like that. So you've got, like I said, you've got oceanographers here, there's geochemists and all these sorts of people. So now you can start actually talking to them about these things because you have different understandings about all these different parts of the jigsaws. So, and hopefully you can see that from the two talks, they're interconnected because, from learning about how mineral dusts affect the albedo of the ocean surface, we think about that from a, can we approach climate change by changing the albedo of that, by us doing something about that. So, again, it's just demonstrated that these things all, they're all sort of topics to start, it sounds a bit preachy, but, just to start conversations, because, if someone's measuring one thing, someone's measuring another thing, sometimes, you're both measuring the same thing from a slightly different perspective. So, that just helps you start unlocking new research questions. So hopefully I've given you something to think about. So thank you for that.
Okay, questions? Comments?
So are there any geochemists in the room? Anybody? No, it's all geophysicists.
I'm a chemist, but I'm not a geochemist.
I'm a chemist.
Yeah.
Just one short question. How much actually the charge influenced the freezing of the particles? If you have a charge on the aerosol or something, did you do some research?
I haven't, but there's a lot of discussions going on, atmospheric charging and things like that. But it's not something that I know much about. I know people who talk about these sorts of things. Are you talking about from cosmic rays, or because there's a lot of experimentation from cosmic rays? There's a huge one at CERN, synchrotron, and to do that, because what they're looking at is the effect of cosmic rays, because it's a very small signal. You have to make sure you've got a very, very clean environment to do that, and that's what they've done at CERN. CERN are very good at making very, very clean labs, so that then they can simulate these things. Because if you've got quite a small signal, you have to make sure that there's nothing else producing that signal, so you can actually say that what you're seeing is down to.
Yeah, that's quite difficult. That's why the cloud experiment is so.
Yes.
But some people were doing like laboratory experiments where they try to see, okay, maybe not so much. Also with the ice, but some of them are pure theoretical, like maybe you heard for Tinsley or such people, which were kind of giving a theory that the charge would help to freeze sooner or change it.
But because we know so little about the underlying freezing processes in the atmosphere, you need to sort of lock them down before you can see the features on the top of them. So, it's like, because there's people thinking about lots of different things, you're always thinking about, well, if we do that, then we can actually do that. The charging, to understand that more, but we have to get up so our fundamental understanding of the freezing processes is sufficient that we know that if there's a charging influence on top of that, we need to know that we really understand this bit before we can. So, but it does mean that it pushes people on to do, yes, let's do this, and then from that we can do the next step.
So first, the basics should be understood better in that sense. So I think that's sometimes questionable. That's why I'm asking this question, because I think that some people made big theories about some things, and this is not very proven in that sense.
So you say Tinsley?
Yeah, there are various groups which were kind of there were also people doing some experiments, but
I suppose by those groups talking to each other, then they go, let's do a joint experiment, and then we can do. Sometimes you have to ensure that everybody's talking to each other, and then let's do a concerted effort in one direction. Or there might be features if someone's doing something theoretical. It may be they're not aware of a certain feature that's come out of in an experiment.
I mean, this is
It could be
now logged topic problem to discuss.
Okay.
One question.
One
In your humble opinion, what is the most important thing for ice condensation nuclei? Size, chemical composition?
But that's people. That's another question that people have got. Now you can get scanning electron microscopes that you can run in environmental conditions, because traditionally they were high vacuum. You can't do any experiments with water in a high vacuum because it just doesn't exist. But now you can do. So now there was a paper last year in Science where people studied and literally filmed water freezing. They're looking for what is the magic spot, and the only way of describing it, is actually magic, because at the moment it's still magic. We don't know whether is it a corner, is it a particular molecular, like you get proteins and antibodies, and they how they interact. So the simplest way, and it also demonstrates the fact that we don't know yet, is just say the magic. What's the magic bit on a mineral that does it, and we're getting close to that by people actually getting these mineral dusts and just looking at them and taking photographs of them as the magic happens, as water suddenly starts to freeze on that. So we are moving in that direction, but at the moment I think I can still call it just magic.
What does that mean?
But if you call it magic, then people want to know. It's magic. That's not good enough for a scientist. They want to know. So if you call it magic, then people go, right, then I don't care, you're magic. That's rubbish. I want to know it. So I almost, magic is quite a positive thing to do, because it makes people think, well, if it's still magic, then it could be my Nobel Prize. Not mine, but they could think, right, then because if you understand it, that's absolutely fundamental science going on.
Is there some effort made on parameterization of IMP in the models in your group?
IMP is slowly going into models, but because because people, it's very difficult to run complex models. They take a lot of time. They take big computers and they take people. And unless you're putting in data that people are confident around, they're not going to waste their time on it. So you've got to get a sufficient set of measurements where people can start to go, right then, I will spend some time changing my model, not doing this experiment, or not doing this study, and do this study for something that someone thinks is quite a nice thing to do. So, yes, but it's certainly not it's not comprehensively being done, because the parameterizations, the bits of information are still coming out of labs and things like that, and there's one lab, and then a year later another lab will come up with another parameterization, but that's still only two, whereas a lot of things that go into models are fundamental physics, or things that people are much more comfortable with, and they're much more happy to commit more time to, where where it's where they don't want to be embarking on something that's so speculative, where they want to look at something that is much more well understood. Because ultimately, when you come with your results, you write them up and they go for peer review, and it's much more difficult to get something through peer review, because if it's reliant on some level of magic, because reviewers are not going to be happy with you using the word magic. There's all sorts of ways. This is still one of our major challenges in our understanding, is just a fancy way of saying magic. But if you write, numerous authors have shown that, the review is going to be much more comfortable with that. So it's a bit of a game, So it takes lots of groups doing things, and then everybody goes, yeah, I think we're all in agreement now. Now let's start putting this into models, because then when people commit time and resource to put it into models.
Thank you.
Okay, I think that we can thank again for your. If someone have some questions, I think that Jim is still available for some minutes. I have one question.
short question. Your presentation, do you plan maybe to put it somewhere online?
I don't know.
It's been recorded for YouTube.
Yeah, but so, as a presentation, as a PDF or something.
I can send it to you if you want.
Okay. Yeah.
Because a lot of
I can also
a lot of the information is just on, you know, I've just amalgamated on things like
I know.
But a lot of
I like some of your slides are really good.
some people are given to people because